Hello there. Tonight, we'll take a slow look at the deepest place on Earth, the Mariana Trench, a long, narrow crack in the floor of the western Pacific Ocean. It runs deeper than Mount Everest stands tall, and at the very bottom sits a quiet stretch of pale sediment called Challenger Deep. We'll travel down through it the way the water does, from the bright surface, through the dim middle layers, and into the cold black where sunlight has never reached. A plain look at a place few people ever see. And by the way, if you'd like more stories like this one, you might want to check out our app. It's called Tonight, and it has fresh stories for you every day, so there's always something new to fall asleep to. Plus, you can hear them in your favorite voice. It's a free download. The link's just below this video. Before we begin, take a moment to settle in. Get comfortable, however that looks for you tonight. When you're ready, close your eyes. Take a slow, deep breath in through your nose, and a long, slow breath out. One more. In and out. Challenger Deep is the deepest known point in the ocean. It sits at the bottom of a long, narrow trench in the western Pacific, called the Mariana Trench. The trench lies east of the Philippines and south of Japan, curving in a long, shallow arc to the east of a small chain of islands. Challenger Deep is at the southern end of that arc, not far from the island of Guam. The trench is long. It runs for about 1,500 miles end to end. It is also remarkably narrow, only about 40 miles wide at most points. If you could see it from above with the water removed, it would look like a long, slender groove cut into the seafloor, with steep walls on either side. Challenger Deep itself is a smaller depression near the southern end. It is a smaller basin, perhaps 7 miles long and a mile or so across at its narrowest, with the deepest point sitting at one end. The seafloor there is the lowest known piece of ground on the planet. It takes its name from the British research ship HMS Challenger, which made the first careful soundings of the area in the 1870s. The crew lowered a weighted rope from the deck and waited for it to touch bottom. They were astonished by how much rope they paid out. Nearly a century later, a second ship, called Challenger II, came back with better instruments and found that the deepest point was even deeper than the first crew had measured. The depth is hard to picture. It is usually given as about 36,000 feet, close to 7 miles straight down. If Mount Everest were dropped into Challenger Deep, with its base sitting on the seafloor, the summit would still be more than a mile underwater. There would be no peak in sight. Light does not reach the bottom of the trench. Sunlight from the surface only penetrates the upper few hundred feet of the ocean in any meaningful amount. Below about 3,000 feet, the water is fully dark, what oceanographers sometimes call the midnight zone, or in the technical Greek-rooted term, the bathypelagic. Challenger Deep lies far below even that, in the lowest layer of all, which scientists call the hadal zone. It takes its name from Hades, the Greek word for the underworld, and it refers specifically to the trenches and other parts of the ocean below about 20,000 feet. Hadal zone water is cold, dark, and under enormous pressure. The bottom of Challenger Deep is not the only place where these conditions exist. There are several other deep trenches around the Pacific, in the Tonga Arc and the Kuril and Japan trenches, but none of them are quite as deep. Challenger Deep is the lowest point of them all. It is also, in a quiet way, one of the least visited places on Earth. Far fewer people have stood at the bottom of Challenger Deep than have stood on the Moon. The precise depth is still a matter of slow refinement. Different surveys using different sonar systems have come back with slightly different numbers. The most recent careful surveys settle on a figure of around 35,876 feet, about 10,935 meters. The uncertainty is on the order of a few feet, which, given the depth, is small. But it is real. The reason the number changes is partly to do with how the depth is measured. Sound waves are used. A ship at the surface sends a sonar ping downward and waits for the echo to return from the bottom. The time it takes for the ping to make the round trip, down and back, tells the survey team how far it traveled. But the speed of sound in seawater depends on temperature, salinity, and pressure, all of which change with depth. The ping does not travel at a single uniform speed, so the calculation has to be corrected for the layers of water it passed through. Small errors in that correction become larger errors over 35,000 feet. That said, the broad picture is clear. The sea floor at the deepest point lies almost exactly 7 miles below the surface of the sea. To get a sense of what that means, a passenger jet at cruising altitude is flying at roughly the same distance above the ground. Imagine sitting at the window of a plane looking down at the cloud cover and the small fields below. Now turn that picture upside down. The water above Challenger Deep is about as thick as the air below a jet. A heavy object dropped from a boat at the surface would take a long time to reach the bottom. Even with weights to help it sink, the descent takes hours. The same is true of a manned submersible. The trip down is slow. The trip up, with ballast released, is also slow. Most of the few visits people have made to the bottom of the trench have used a full working day for the round trip, with only a short window of time actually spent on the seafloor itself. It is worth pausing on the scale a little more. The deepest part of the ocean is a great deal deeper than most people imagine. The average depth of all the world's oceans, taken together, is about 12,000 feet, less than half the depth of Challenger Deep. Even most of the famous deep places in the sea, the ones often mentioned in nature programs, lie at only a fraction of that depth. The abyssal plain, the vast flat seafloor that covers much of the open ocean, sits at about 15,000 feet. Challenger Deep is more than twice that. And yet, the deep ocean as a whole is still a thin film in the planet's own terms. Even 7 miles down is a tiny fraction of the way to the center of the Earth. The Earth's radius is nearly 4,000 miles. Challenger Deep, deep as it is, only scratches the outermost skin. Almost all of the planet is rock below the seafloor, not water above it. So how does a place this deep come to exist at all? The answer is a slow, steady process that has been going on for millions of years and is still going on now. The Mariana Trench is a subduction zone, a place where one of the great plates of the Earth's surface is sliding down beneath another. To understand the trench, it helps to walk through the process step by step. The first thing to know is that the outer skin of the planet, the crust and a little of the layer beneath it, is broken into large slabs called plates. These plates fit together a little like the panels of a football, and they move very slowly against each other. The movement is on the order of a few centimeters a year, about as fast as a fingernail grows. It is too slow to see. But over millions of years, the plates rearrange the surface of the Earth completely. Some plates carry continents on top of them. Others are mostly under the sea. The plate beneath the western Pacific is mostly ocean. It is old and dense and cold. To the west of it sits the Philippine plate, which is a little younger and a little lighter. The next step is what happens when these two plates meet. The Pacific plate is being pushed slowly westward, driven in part by the spreading of the seafloor far to the east, where new crust is being made along the mid-ocean ridges. As it moves west, it eventually runs into the Philippine plate. When two plates meet, one usually goes down beneath the other. The denser plate sinks. In this case, the dense old Pacific plate slips down beneath the lighter Philippine plate. The point at which it begins to bend downward is the trench itself. The plate is being pulled downward by its own weight into the hot rock of the mantle below. So the trench is, in effect, the bend in the slab. It is the place where one plate folds down and disappears beneath another. The seafloor on the Pacific side curves over the edge and starts its long descent into the interior of the planet. The trench is the trace of that bend, drawn on the seafloor. This also explains why the trench is so narrow. It is narrow. It is a fold line, a long, thin scar in the crust where the plate is tipping over. The walls of the trench are steep because the plate is bending sharply. The bottom is narrow because the bend itself is narrow. The descending plate carries seawater and sediment down with it. Far below, in the hot mantle, the water gets cooked out of the rock and rises into the overlying plate, where it lowers the melting point of the rock above it. The melted rock rises further still and reaches the surface as volcanoes. This is why, parallel to the trench and just to the west of it, there is a long, curved chain of volcanic islands. The Mariana Islands themselves, Guam among them. The trench and the islands are part of the same system. The trench is where the plate goes down. The islands are where some of what it carries comes back up. The whole thing is slow. The Pacific plate moves into the Mariana Trench at perhaps a few centimeters a year. The trench itself has existed in something like its present form for tens of millions of years, and will continue to exist for tens of millions more. One of the most striking things about Challenger Deep is the pressure. Water is heavy. A column of seawater 7 miles tall presses down on the seafloor with a force that is hard to imagine. At the bottom of the trench, the pressure is over 1,000 times what it is at the surface, about 16,000 pounds per square inch. That is roughly the weight of a small car, pressing on every square inch of any object resting on the seabed. For a long time, scientists were not sure whether anything at all could live under such pressure. The early belief was that the deep ocean must be sterile, too cold, too dark, and under pressures too great for life to manage. That belief turned out to be wrong, but the reasons it was wrong are interesting. Pressure does strange things to matter. At the depths of Challenger Deep, water itself is slightly compressed. It is denser there than at the surface, not by a great deal, but enough to matter. The water at the bottom of the trench is a fraction of a percent denser than the water above. If you could lift a cubic yard of it up and weigh it at the surface, it would be slightly heavier than a cubic yard of surface seawater. A small thing, but real. The pressure also affects gases. Most gases dissolve into water more easily under pressure. The deep sea holds dissolved oxygen and carbon dioxide in ways that the surface ocean does not. Some chemical reactions run differently. proteins in living tissues can be deformed or stiffened. This is the central problem that life at these depths has had to solve. The proteins inside ordinary surface-dwelling creatures begin to fail under deep-sea pressure. They lose their shape. The cells stop working. A surface fish brought down to Challenger Deep would not survive. But hadal organisms have evolved differently. They make proteins that are designed to keep their shape under deep-sea pressure. Some of them also produce small molecules, chemicals known as piezolites, that act in effect as a kind of internal scaffolding, helping to keep proteins folded properly when the pressure is high. The same molecules, in lower amounts, are found in many ordinary deep-sea creatures. In hadal creatures, the concentrations are higher. This is one reason why, when a deep-sea fish is brought up too quickly to the surface, it does not always look the way it does on the seafloor. The change in pressure can cause its tissues to swell, its eyes to bulge, its body to lose shape. The fish itself was not deformed at depth. It looked down there like an ordinary fish. The deformation happens during the trip up. In its home, under pressure, the hadal fish is calm and slow. Its body is built for the place where it lives. The pressure doesn't trouble it. It is simply the condition that the creature lives in. For people, the pressure remains the great barrier. The pressure is too great for any human body to withstand directly. The only way down is in a vessel built to hold the pressure off. A sphere of thick steel or titanium, designed to keep the sea on the outside. The walls of these vessels are several inches thick. Even so, the load on them is enormous. Designing a vessel to make the trip is a serious engineering problem, and not many have ever been built. So what does the floor of Challenger Deep actually look like? The handful of expeditions that have reached the bottom have brought back photographs, video, and physical samples. The picture they have built up is consistent. The floor is mostly pale and soft. It is covered in a fine sediment, a deep layer of very small particles that have settled out of the water above over a very long time. This sediment is sometimes called marine snow when it is still in the water column, drifting downward. On the sea floor, packed together over millions of years, it forms a soft, pale ooze. The particles are tiny. They include the shells of microscopic plankton that lived near the surface and sank when they died. Fine dust blown out to sea from distant continents, and the chemical debris of slow seawater reactions. The dominant component in the Mariana area is a fine clay. There are also flecks of organic matter, the slow rain of dead surface life, though by the time it reaches the bottom, most of the soft tissue has been eaten or broken down. Photographs from the seafloor show a soft, slightly rolling plain. There are no boulders, no jagged rocks. The sediment is too thick. Anything that fell in long ago has long since been buried. The surface of the ooze is marked here and there with shallow tracks. Long, thin trails where some small creature has crawled across the bottom. There are little pits and mounds where worms or other small animals have burrowed. There are sometimes scattered black specks, manganese nodules, slowly accreted lumps that take millions of years to form. The walls of the trench are different. Up the steep sides, the rock of the descending plate sometimes shows through. There are exposed cliffs and outcrops of basalt the dark volcanic rock that forms the floor of the ocean. There are also patches of pale limestone, made of the compressed shells of long-dead plankton. In places, the walls show fault lines, long cracks where the rock has shifted as the plate has bent. But at the very bottom, in the flat central trough, it is mostly sediment. Soft, pale, uniform. The view from a submersible window, with its bright lights on, shows a slow, gentle landscape, much like a field of fresh snow under a low spotlight. There are no shadows of mountains or hills. The horizon, such as it is only a few feet away. Beyond the reach of the lights, everything is black. Above the seafloor, the water itself is very clear. It carries very little suspended material. Marine snow drifts down, slowly, like falling dust. A submersible's lights pick up the slow particles as they pass through the beam, and they look like snowflakes in a winter night. The floor itself does not move quickly. There are slow currents, but they are gentle. The sediment is not stirred up easily. A footprint or a track left on the floor of Challenger Deep would stay there for a long time. Possibly centuries, possibly longer. The tracks left by the early submersibles in the 1960s may still be visible today. It is a very quiet landscape. The sound there is the slow, low-pressure rumble of the deep ocean, and the soft mechanical sounds of any vessel that happens to be visiting. Otherwise, nothing. For all the cold, the dark, and the pressure, the bottom of Challenger Deep holds life. Life is there. Not abundant by surface standards, but real. The most often photographed of the visible creatures is a small crustacean called an amphipod, a kind of small shrimp-like animal. Amphipods are common throughout the ocean, but the species that lives in the deepest trenches has evolved to be larger than its shallow cousins. Some hadal amphipods are several inches long. They are pale, almost colorless, with long, sensitive antennae. They scavenge whatever sinks down. The slow drip of dead organic matter from above, the occasional larger body that falls and lands on the floor. There are also fish. The deepest known fish, photographed in the Mariana Trench, is a kind of snail fish, a soft, pale pink, gelatinous creature about the size of a hand. It is gentle and slow. It has no scales. Its body is mostly water and soft tissue. It does not need a hard skeleton because the pressure of the surrounding water supports it from outside. Snailfish have been photographed at depths well over 26,000 feet in the Mariana and in neighboring trenches. There are sea cucumbers, the long, soft cousins of starfish, which drag themselves slowly along the sea floor, eating the sediment as they go. There are anemones, attached to rocks and to bits of debris, with thin, pale tentacles extended into the water. There are small worms in the sediment, and microscopic creatures called foraminifera, which build tiny shells of organic and mineral matter. And there are bacteria, vast numbers of them. The sediment of Challenger Deep and the water just above it is rich in microbial life. Many of the microbes there are not closely related to surface bacteria. They live slowly on tiny amounts of energy, sometimes processing chemicals that other organisms cannot use. Some of them break down the carbon that drifts down from above. Others run on chemical reactions that, at the surface, would barely run at all. The food supply at the bottom is thin. Almost everything that lives at hadal depths depends, in the end, on the surface ocean far above. Sunlight at the surface feeds the plankton. The plankton are eaten by other creatures. Those creatures die, and a small fraction of all that organic matter drifts down. By the time it reaches Challenger Deep, almost all of it has been intercepted and eaten along the way. What arrives at the bottom is a slow, thin rain. Occasionally, something larger falls. A dead whale, sinking, may eventually reach the deep. When it does, it is the equivalent of a great feast. Hadal amphipods and other scavengers find it within hours. They strip it. The bones are colonized by specialist worms that can digest the rich fats locked in the marrow. A single whale fall can sustain a small community of deep-sea life for years. But these are rare events. Most of the time, the floor of Challenger Deep is a place of slow, patient creatures living on small amounts. They do not move quickly. They do not waste energy. They are built for endurance, not for haste. The pace of life there is matched to the pace of the food, and both are slow. The first people to reach the bottom of Challenger Deep did so in January of 1960. The vessel they used was called the Trieste, a kind of submersible known as a bathyscaphe. It was an unusual machine. The Trieste had been designed by a Swiss physicist named Auguste Piccard, who had earlier made his name in stratospheric ballooning. The bathyscaphe, in effect, was an underwater balloon turned upside down. It had a large, lighter-than-water float, filled with gas being lighter than water, and roughly incompressible, so that it kept the vessel buoyant at any depth. Slung beneath the float was a small steel sphere, a pressure cabin, just big enough for 2 people to sit inside. To go down, the crew released some of the buoyant gas and added ballast. To come back up, they released the ballast. On the day of the dive, 2 men were in the sphere. Jacques Piccard, the son of the designer, and Don Walsh, a young officer in the United States Navy. They left the surface vessel in the morning and began the long descent. The trip down took nearly 5 hours. The vessel sank slowly through layer after layer of the ocean. The light dimmed, the temperature dropped, and the pressure rose. The crew watched the depth gauge climb and listened to the small creaks of the sphere adjusting to the pressure. About 600 feet above the seafloor, there was a small cracking sound. A plexiglass viewport in the outer compartment had given way under the pressure. The pressure sphere itself, where the men sat, was unaffected. They considered the situation and continued the descent. A little before 1 in the afternoon, the Trieste reached the sea floor. The depth gauge, slightly miscalibrated, read about 37,000 feet. The actual depth was a little less, but still close to 7 miles. The two men sat in the sphere, looked through the small viewport, and saw the floor of Challenger Deep for the first time. It was, by their accounts, soft and pale. A small cloud of sediment had been raised by the vessel's landing, and it took a little time for the water to clear. When it did, they could see the floor stretching away beyond the lights. Picard later reported seeing a flatfish, a sole or a flounder, though this observation has since been doubted. It may have been a sea cucumber or some other creature. They stayed on the bottom for about 20 minutes. They ate a small meal, a chocolate bar each by some accounts. Then they released the ballast and began the long ride back to the surface. The journey up took just over 3 hours. When the Trieste broke the surface that evening, it was alone in a wide and quiet ocean. The support ships were nearby. The men climbed out, tired and cold, and the vessel was eventually towed back to port. For the next 52 years, no one returned to the bottom of Challenger Deep. The Trieste herself was retired. The deep, having been touched, was left alone again. In 2012, the film director and ocean enthusiast James Cameron made a solo dive in a different vessel, a green-painted one-person submersible called the Deep Sea Challenger. Since then, a small number of other dives have been made, mostly in a newer titanium-hulled vessel called the Limiting Factor. The total number of human visits to the bottom of Challenger Deep remains very small. The dives since 2012 have done what the original Trieste expedition could not. They have lingered. The newer vessels can stay on the seafloor for hours, not minutes. They carry better lights, cameras, and instruments. They have brought back the pictures that we now use to imagine the bottom of the trench. One of the things the modern visits have confirmed is that Challenger Deep is not a single point. It is a small basin with several deep spots. There is an eastern pool, a central pool, and a western pool. The deepest of the three, in the recent surveys, is the eastern pool. The differences in depth between them are small, a matter of a few feet, and the deepest point can shift slightly between surveys as the maps are refined. But all three are part of the same long basin. The modern dives have also begun to catalog the life on the bottom in more detail. The hadal snailfish was first photographed there in the 2010s. Various species of amphipod have been collected and brought up. Sediment cores have been taken. Microbial samples have been carried back to laboratories on land, where they are still being studied. Some of those microbial samples have been interesting in unexpected ways. The deep-sea bacteria produce molecules that are not produced anywhere else, and a few of them are being studied for possible use in medicine or industry. The pressure-resistant proteins of hadal creatures are being studied for what they reveal about how proteins fold and unfold under stress. The ecosystem at the bottom of the trench, small as it is teaching us general lessons about life under difficult conditions. Modern dives have also brought back something less encouraging. They have brought back small pieces of plastic, bits of bag, fragments of packaging, the occasional length of fishing line. Even at the deepest known point of the ocean, the slow rain from above includes the debris of human life on the surface. It is a quiet finding, not a dramatic one. Small fragments, not heaps. But it is there. Plastic, once it has reached the deep, does not easily go away. The newer vessels themselves are quiet and slow. The limiting factor is a small titanium sphere with 2 seats inside, fitted to a more streamlined hull than the old Tree Este. It is designed to be used repeatedly. It descends at a steady rate, several hundred feet per minute. It carries its own life support, its own lights, its own scientific instruments. Inside, the air is dry and slightly cool. The viewports are small and round. A pilot inside the limiting factor, on the way down, would watch the depth gauge tick steadily upward. The water outside the viewport would dim from blue to black within the first half hour. After that, there is nothing to see outside the cabin, except what the vessel's own lights pick out when they are switched on. Most of the descent is made in the dark, with the lights off to save power. The vessel sinks through nothing but black water for several hours. Then, at the bottom, the lights come on, and the soft, pale floor appears below. The pilot eases the vessel down. The sediment puffs up gently and settles. The slow current carries it away. The lights pick out the small tracks and pits in the soft floor. A pale amphipod might drift past the viewport, drawn by the disturbance. The vessel sits quietly, and the work begins. The water at the bottom of Challenger Deep is cold, not freezing. It is salty enough that it stays liquid, but cold. The temperature is just above the freezing point of fresh water, somewhere around 34 to 36 degrees Fahrenheit. It doesn't vary much. The hadal zone is one of the most thermally stable places on the planet. Whatever the season above, the bottom of the trench is the same. The cold comes from far away. Most of the deep ocean water in the world is filled, slowly, by cold, dense water that sinks from the surface in the polar regions, in particular around Antarctica and in the North Atlantic. This water is cold, salty, and dense, and when it forms at the surface, it sinks. Once down, it spreads out across the floor of the ocean, very slowly, taking centuries to make its way around the world. The bottom water in the Western Pacific has been on this long, slow journey for a very long time. By the time a particular parcel of water reaches Challenger Deep, it has been out of contact with the surface for perhaps 1,000 years. It has carried only its temperature and salt down with it, and a small load of dissolved oxygen that it picked up at the surface long ago. There is, in fact, oxygen at the bottom of Challenger Deep. Not as much as at the surface, but a real amount. This is one of the reasons life is possible there. The oxygen was brought down by the deep, cold currents and is used, very slowly, by the creatures and microbes living on the floor. Currents in the trench are slow. The deep ocean is not still. There is movement everywhere, but the speeds are small, a few centimeters a second in most places. The water moves at the pace of a slow walk. The slow rain of marine snow drifts with the current, drifting slightly to one side as it falls. Inside the trench itself, the currents are gentler still. The narrow walls slow the flow. The water at the bottom turns over very slowly. New water enters from the open ocean at the top and gradually replaces the old. The full turnover may take many decades. These slow currents do a few quiet jobs. They bring oxygen down, carry waste products away, and smooth the sediment, very gently, over very long times. They occasionally bring a piece of food, a sinking carcass, a fragment of wood, into the trench from the open ocean. The sound of the water down there, if we could hear it directly, would be a low, slow rumble. The pressure makes the sound itself behave a little differently. Sound travels faster in deep water than in shallow. A whale call made near the surface can travel for thousands of miles through certain layers of the deep ocean, the so-called sound channels, where sound waves bend and stay. Some of those calls would, in principle, reach the rim of the trench. Almost none of them would reach the bottom. The bottom of Challenger Deep is one of the quietest places known. There is no wind, no rain, no surf, and no machinery, except very rarely, when a submersible visits. The only sounds are the very slow movements of the water itself, and occasionally, the small mechanical click of an instrument left there by some previous expedition. There is still a great deal that is not known about Challenger Deep. The number of visits has been small. The total time that human eyes have spent at the bottom of the trench is, when added together, only a matter of days. The seafloor area examined directly is tiny, a few square miles, scattered across a basin that is hundreds of square miles in size. Most of it has never been seen. Many of the species that live there have not been formally described. New amphipods are still being found in the sediment samples. New microbes are still being identified from the water samples. The full inventory of life at the bottom of the Mariana Trench is, after 60 years of work, still incomplete, and may remain so for a long time. The geology, too, has more to give. The walls of the trench have not been mapped in detail. The chemistry of the sediment is only beginning to be understood. The way the descending plate behaves, exactly how it bends, exactly how its surface deforms, is the subject of ongoing study. And there are open questions that are simply hard to answer. How does the deep food web work in detail? How do hadal creatures find each other to breed when food and mates are so sparse? How do the slow currents inside the trench shape the distribution of life? These are not puzzles of the dramatic sort. They are quiet, open questions, the kind that take patient work to answer. What is clear is that Challenger Deep, far down at the bottom of the world's seas, holds life. It is slow and dark and cold and under enormous pressure. But it has water and oxygen and food in trickles. There are creatures, soft and pale and patient, and microbes by the trillion. It is a place where life manages to keep going in a way that fits the conditions. It is also a place that has always been there, in something like its current form, for a long time. The trench has been opening for tens of millions of years. The bottom has been sitting at roughly its current depth for most of that. The slow rain has been falling for all of it. The amphipods have been walking their tracks for thousands of generations. Far above, on the surface of the western Pacific, the sea looks like any other sea. A long, calm blue swell rolls in. A few clouds drift in the sky. A passing ship, perhaps, or a small flight of seabirds. There is nothing to mark the trench from above. The water there looks just like the water everywhere else. And yet, 7 miles straight down, the floor sits where it has always sat. It is pale and soft, marked with thin trails, lit only when a vessel happens by, and otherwise dark. The slow currents drift on. The marine snow drifts down. The amphipods move quietly across the sediment. Far below, the trench floor lies quiet and dark.